Okay, so we have used some of the logarithm rules to like expand and simplify. Rebecca, can you move back to your desk there? Now we're going to be taking a look at solving exponential equations. So solving for x and finding answers to equations using logarithms. So firstly, exponential functions can be written in many different ways, and it's very helpful to have the skill of being able to express things with like a particular base. So we're going to practice with the base of 2 here. I want to express each of these as just a single base of 2. So 16, how do I express this as a base of 2? So 2, Sam? To the power of 4. Okay, perfect. 4 squared. So 4 to what exponent? So how can I express this? Base of 2. Kenzie? 2 to the 2 to the 2. And then I can multiply these, right? This would be, again, 2 to the 4. So I'm just expressing 4 as a base of 2. Okay, C, square root of 16. I think that's 4. We'll just express that firstly as 4. And then 64, so the 6th root of 64 cubed is 64 to the 3 over 6. And 64 to the 3 over 6, that's actually 64 to the exponent half, which is really just the square root of 64. So square root of 64 is actually just 8. And then if we wanted here, we can express each of these as bases of 2. This is 2 to the 2 and 2 to the 3. So I'll just keep the base and add the exponents, 2 to the 5. Okay, 14, not as easy, because 14, that's like some kind of decimal value. So what we're going to do is we'll express this with the question we want to answer, which is 2 to what exponent? So 2 to some exponent. We want to know when that's equal to 14. And I would like to express this exactly as a base of 2. So no rounding, no decimals, no anything like that. Okay? So here's what we're going to do. We're going to express this in logarithmic form. So switching from exponential into logarithmic. So practicing that skill again, it will be log base 2 of 14 equals x. And then if we wanted to actually calculate this, which we're actually not going to, but we would express this using the change of base formula as log 14 over log 2. So if I want to express 14 with a base of 2, I'm actually going to take this and I'm going to sub it back into the exponent. So 14 will actually be equal to 2 to the exponent log 14 over log 2. Or if you want, you could even express it as a single logarithm like that. So this is my answer. This is 2 to the base, 14 expressed as a base of 2. 2 to the exponent log 14 over log 2. So we can actually do this with any number, right? So part D is showing us that any positive number could be expressed as a power of any other positive number. So 14 can be expressed with a base of 2. I can express 27 with a base of 5, right? Whatever I want, as long as we express it like this. Okay, and we're expressing it exactly as well. We're not rounding anything or like calculating any decimals or anything like that. So we're expressing this as an exact value. Amelia? Why are we not? Because this is a decimal, and we're expressing it exactly as a base of 2. So by not calculating it, we're expressing it as an exact value. If we calculate log 14 over log 2, and I round it, then it's no longer a perfect expression, right? It's no longer exactly equal to 14, because I've rounded it. But if I wanted to know approximately what that exponent was, I could calculate and just sort of see around where it is. Okay, so we are going to solve some exponential expressions. The first couple that we're going to do, we're going to create like bases, so common bases, and we're going to use this rule that we've talked about before, which is if I have two like bases to some exponents, then I know the exponents must be equal, and then I can use that to solve the exponents. So I want to know 3 to x plus 6, when is that equal to 81 to the x? So what is x to make this expression equivalent? So 81 is the higher number. Can I express this as a base of 3? 3 to what exponent equals 81? 3 to the 4 equals 81. And then I'm going to use power rule here with exponents. So 3 to the x plus 6 is equal to 3, and then 4 times x is just 4x. Okay, so create a common base. Simplify the exponents as much as possible. And then this rule says that if my bases are the same, x and x, which these ones are, 3 and 3, then I can set the exponents equal to one another, because there's no other way that these expressions will be equal if they're the same base, unless the exponents are equal. So I know that x plus 6 must be equal to 4x in order for this expression to be true. So I'm going to say x plus 6 must be equal to 4x, using the rule above. And can I solve for x now? Yep. So I'll bring that x over. I'll have 4x minus x. That's 3x. And then, of course, x equals 2. So I'm not just ignoring the 3's, guys. Sometimes I have students ask me questions about this, and they'll say, so we just get rid of the 3's, right? Kind of, but not really. We're basically just using logic to say that if 3 to the something equals 3 to the somethings must be equal. Okay, so if the bases are the same, the exponents must be equal. That's the logic that we're using. Okay, so there's not some math magic happening here where we're just getting rid of the 3's. We're just using mathematical logic, or just problem solving and logic to jump to the next step here. Okay, so let's try it with example B here. So 32 is the higher number. Let's see if we can express 32 as a base of 4. Can we? So 4 to what exponent equals 32? I don't think we can. Is there something lower that both of these could be expressed as the same base? Clayton? Okay, so let's express both with a base of 2. So 4 is 2 to the 2, and then it still has a 2x. How about 32? What is 32 as a base of 2? Kenzie? 2 to the 5. And then I still have x minus 5 as an exponent here. Okay, so let's simplify. I'm going to keep the base, and these are power rules, so I'm going to multiply the exponents. So I'll have 2 to the 4x. And then be careful, when I multiply 5 and x minus 5, I'm multiplying both of those terms in x minus 5 by 5. So it will be 5x minus 25. Or just keep it in bracketed form, right? 5 times x minus 5 in brackets. So now that we have common bases here, we know the exponents. If 2 to the something is equal to 2 to the something else, we know the somethings have to be equal, right? So we can set the exponents equal to one another and just solve for x. So 4x must be equal to 5x minus 25 for this statement to be true. Okay, so I'll move the 5x over. We will get negative x equals negative 25, which must mean x equals 25. How can I check my answers for both of these? Emma? Plug it back in. Make sure you get left side equals right side. Okay, very straightforward. We sub back in for both x's here. Put it in for 2. Is 3 to the 8 equal to 81 to the 2? Because it's x plus 6, right? Check and make sure that they're equal. If they are, I know that I found the right answer. If they're not, something went wrong somewhere along the way. Okay? So for all of these, we will sub back into check. So back into the original equation. I do not know how my just changed colors on me. Any questions on these two so far? Okay. So here's a bit of a different example. When you have powers in your equation with different bases, it's difficult to write those with the same base, right? Some of them, it's easier, right? 4 and 32, 5 and 25, something like that, 5 and 125, anything like that. But if it's not easy, like we have 2 and 5 in this example here, sometimes it would actually be easier to solve by taking the log of both sides. And then we will apply the laws of logarithms to remove the variables from the exponent. So we'll apply the power law. Of logarithms to remove the variable from the exponent. All right, so in the case where it's very hard for us to create common bases, 2 and 5, we will go with this method. Usually it's easier to create common bases, so if possible, you'll go this route. If not possible, then we'll follow these steps over here. So we're going to start by taking the log of both sides. I know that the base and exponents on each side are isolated, so I can do that. Okay, so take the log of both sides. We will use power law. So power law says we're going to bring this down. We can actually do it for both of them. Bring it down as a multiple. Remember, I can only do this if I have the log of something to an exponent. Then I can use power law. So we'll bring it down. I always write it in brackets here because technically it's that whole thing times the log of 2. And this whole thing times x plus 1, right, times the log of 5. So that's power rule. Okay, and if I'm going to start getting x's by themselves, I sort of need to expand and kind of move things that have x's to one side, move things that don't have x's to the other side. So I'm going to bring this log of 5 into here and this log of 2 in here. So I'll have 3x times the log of 2 minus 2 log 2. And that's going to be equal to x times the log of 5 plus 1 times the log of 5, so just plus log 5. Use distributive property. Anything that is attached to an x now, we're going to move this to one side. Anything that does not have an x with it, you move it to the other side. I usually try my best to get rid of as many negatives as I can in the expression. So this one is negative. I mean, this one will become negative when we move it to the other side, so there's not a lot that I can do to eliminate. But if I had like tons of negatives, I would try to move things to the sides that make the least number of negatives. It doesn't really matter, but that's probably what you will see. If you have a slightly different answer with different negatives and positives, that's probably why. Okay, so I'm moving everything to the left with an x, so it will become negative x log 5. Remember to switch the sign of that expression when you move it over. And then I'm going to have log 5, and negative 2 log 2 will become positive 2 log 2. So my ultimate goal here is solve for x. Get x by itself. That's the goal, right? Solve and find out what x is. So I have an x in this term, and I have an x in this term. I'm actually going to common factor the x from both terms, which means I will take it and write it out of a set of brackets here. So I'm dividing both of these by x, common factoring, and I'll be left with 3 log 2 in the first expression minus log 5 in the second expression. So common factor, that's the next step. Done. And then our last step is get the variable by itself. So I have x times this whole expression. I'm just going to divide this whole expression on each side so that it cancels. So this is gone, x is by itself. So x must be equal to log 5 plus 2 log 2 divided by 3 log 2 minus log 5. Done. Okay, I'm actually just going to leave it there. We do know that maybe we could simplify this expression a little bit. Like if I brought this 2 up and then merged the logarithms and all of that kind of stuff, I could do that, but this is fine. Okay, so if you guys want to check this, what you would do is you calculate this decimal approximately, leave 3 or 4 decimals on there, and you sub it back into your original answer. Check that left side is very close to your right side. The more decimals you leave, the closer your left side and right side will be. Okay, so I can still sub this in to check. Can I clarify anything for this example? Zach? So I'm going to calculate this whole thing on my calculator. So why don't we try it together? We're going to evaluate log 5 plus 2 log 2. Remember, guys, if your calculator opens a bracket after you do log 5, make sure you close your brackets as you're doing this. So evaluate the top. Press equals on your calculator. You should get 1.301 something. Divide by, in brackets, 3 log 2. Close up a bracket if your calculator opened that when you put in log. Minus log 5. Close up your bracket. You should get 6.3738. And then that's what you're going to sub back into your original equation. So I'm going to sub 6.3738 in here and here, and check that my left side and right side are equal once I calculate. Does that answer your question, Zach? Yeah. Okay. Okay, I want you guys to try the process on B. See if you can follow along with it. See if you can solve. I'm going to give you a couple minutes head start to do this. Clayton, why didn't you tell me? Yeah, lost his position.
Does anyone else help you?
Okay, so here's our solution here. Follow along with the steps. Again, either answer is fine, whatever you have. If you calculate both of those as a decimal, they'll be the same. Okay, can I answer any questions on this one? Nick? Same thing. Yep. So as long as the log 2 is positive and the log 3 is negative, it doesn't matter the order. Amelia? Either one of those is fine. It's the same. Okay, the last part that I want to do here, actually, sorry guys, I just need to read. All right, so we're going to do example 4 and 5 next class. Example 6, I just wanted to introduce to you guys sort of like a bit of a new notation that we're using in grade 12. You'll see this again in calculus and vectors when you do, or if you decide to take calculus and vectors, you will see some of these formulas when you do some applications. So these are basically the same as our y equals a times b to the x formula, except they're in function notation. And they're sort of set up specifically for half-life questions, doubling questions, and then percent growth or decay type questions, so interest or any kind of growth or decay. Think of this as your y, think of this as your a. In this case, b is 2, because it's like only for doubling questions. And then this is total time over capital D, which represents the doubling period, which is here. Capital D is doubling period. Okay, and then same thing here. We say a at t, which is just like amount at time t. That's like our y. This is this little a with the subscript of 0. It's like a initial. So initial amount, a to the subscript of 0. This is like your b, but it's for specifically a half-life question. And then again, t is your total time. And h represents that half-life period. So how long a half-life takes. Okay, and then this is very similar to our compound interest. So this is just, again, for percent growth or decay. We will add for growth and subtract for decay. So you choose which one you're going to use for that, either plus or minus. And again, this is like your y, this is like your a. This is sort of like your b, this whole thing here. And then this will be like time in years usually, but total time. Okay, so it's the same as before. It's just like a slightly different notation because we haven't really been using function notation. We've been using y equals notation. So I just wanted to introduce these to you guys. You may see them again in your math travels if you decide to go on past this course. So you do sort of need to be familiar with them. But we're going to use them the same way that we use y equals a times b to the x. Okay? So, for instance, a bacteria culture doubles every 15 minutes. How long will it take for a culture of 20 bacteria to grow to a population of 163,840? So we are going to use the a at t doubling formula, which is future amount at time t is equal to the initial amount. And then we're just going to put right in the doubling. And then it will be time over doubling period d. So what do we know out of each of these here? Do we know a at t, future amount? Keaton?
I was just going to say D is 15.
D is 15 minutes. Clayton?
163,840.
Okay, that's future amount. Do we know initial amount, a initial? Sarva? 20 bacteria culture is what we start with. And do we know total time t? That's our question mark, right? That's what we want to find. So let's just plug these in here. We'll have 163,840. We will start with 20. And then the 2 is already in there for us because it's doubling. And it will be t over d, 15 minutes. Okay, so literally we ended up here with something that's the exact same as our y equals a times b to the x formula, right? It's no different than what we've done before. Zach? Yeah, so it's a subscript, and usually when we would say something like with a subscript of 0, it just means like the initial value. So this just means the initial amount. Okay, so you guys are just going to solve from here as usual. So I should know if I'm going to end up solving for an unknown in the exponent, I will have to use log to help me with that. What's the first thing that I need to do in a question like this, though? Sam? Okay, get the base and exponent isolated. So we're going to start by dividing 20 out. I think this should be an exact value here. Perfect. If it wasn't, you leave in fraction format. And then you have a choice. You can use the change of base method or you can use the power law method, whatever you want. Okay, so I think in the past we've done log of both sides. Once the base and exponent are isolated, then I can bring down the exponent and write it as a multiple. Okay, we're going to be sort of reviewing some of these application type questions throughout this unit, but we'll also do a couple full lessons doing some more application stuff. Okay, so same process as grade 11, just reminding ourselves of this, or for some of us, we're re-practicing some of this for the first time. So divide out the log of 2. We're trying to move everything away from t now. Notice I haven't used my calculator yet. I'm going to use my calculator at the very end when t is by itself. Why? Why don't I use my calculator all the way through each step here? Rebecca? Yeah. So, Clayton, did you want to add to that?
I was just going to say, so when I do these, if I get a whole number, I usually just simplify in this, you get 13.
Sure.
And do it like that.
Yeah, so if you were happening to get whole numbers all the way down here, that would be fine. But I would just say, like, in general, a lot of times we don't get whole numbers. So in those cases, we would leave it until the very end. But yeah, if you happen to calculate it and you notice, like, oh, log of 8192 divided by log 2 is actually just 13, then go ahead and put in 13 for sure. That's no problem. So this will be 15 times 13 then. So that would be 195. Okay, so you're going to calculate this. Or you can calculate this and then just times your answer by 15, whatever you want to do. Units of measurement here for time, what would that be? Clayton?
Minutes.
Minutes. Why?
Because 15 is in minutes. That's what we do originally.
We entered the doubling period in minutes, so we would expect to get our time also out in minutes. That would make sense. So therefore, it takes 195 minutes. For the culture. To reach 163,840 cells. All right.